Urantia University, Paper 41, Lecture for Week 3. Section 5, Solar Radiation. The authors speak of the pressure exerted by light and X-rays within the Sun. This pressure is well known to our physicists. Light pressure on satellites would cause them to drift out of their assigned places in orbit if this pressure was not compensated for. And recently Japan orbited a solar sail that could propel itself through space using the pressure of light on the surface of the sail. But the statement about the worth of sunlight takes some thought. The authors state, as you value energy and power on your world, sunlight would be economical at $1 million a pound. Though photons have no rest mass, they have energy, and energy is equivalent to mass. It is possible to calculate the energy of a photon and convert that to mass. Knowing the equivalent mass of a photon, it's possible to calculate the number of photons in a pound, and then to calculate the energy in a pound of photons. Perhaps a student would wish to do this, but remember that the answer is probably not $1 million, since the authors say, economical at $1 million. Paper 58 also has some information about the worth of light energy. Quote, if the light falling upon North America were paid for at the rate of 2 cents per kilowatt hour, the annual light bill would be upward of $800 quadrillion. Chicago's bill for sunshine would amount to considerably over $100 million a day. Unquote. Slide 3 shows the calculation of the cost of electricity in a day falling on Chicago at a cost of 2 cents per kilowatt hour. The figures used for the power of sunlight and the calculations were found on the internet. The figure given in the Urantia book is in the same ballpark as the calculated figure. The area used for Chicago is a modern number. Chicago may have been smaller in area in the 1930s, and this could reduce the cost of sunlight for one day closer to the $100 million cited by the authors. Paragraphs 4 and 5 of this section are somewhat problematic. In paragraph 4, the text refers to an X-ray stimulated electron being able to warm an inhabited planet. This paragraph seems to refer to photons as electrons. In fact, the word photon doesn't appear in the Urantia book. It's true that our sun emits electrons as well as other charged particles, but it's photons in the infrared range that warm surfaces. And in paragraph 5, the text refers to agitated electrons that are emitted by a sun. But note in the last paragraph, the authors refer to sunbeam rather than electrons. It's interesting that Eddington also does not use the term photons in his book Stars and Atoms, which book may be the source for much of paper 41. But Eddington does not say that sunbeams are agitated electrons. He says that light rays are Hertzian waves that escape the sun. Hertzian waves are electromagnetic waves such as X-rays, visible light, infrared light, microwaves, etc., as can be seen on the current slide. A photon is the particle character of light. A wave is the second way light manifests. The difference between a photon and an electron is very significant. An electron has a rest mass. A photon does not. Photons travel at the speed of light. Electrons cannot. The mass of an electron increases without bounds as the electron is accelerated ever closer to the speed of light. In the rest of section 5, the authors discuss the dual nature of light, which I previously mentioned. In paragraph 7, the authors say that the particles of material existence traverse space like a fusillade. Here they seem to be speaking of photons. In paragraphs 7 and 8, the authors discuss the wave manifestation of light under certain conditions. They say that the wave phenomena are due to the interaction of the stream, to the mean stream of photons, with energy fields in the universe. In paragraph 8 of this section, the authors again reiterate that the wave-like character of light is due to interactions with energy fields, but they also state that the light appears to be chopped up into infinitesimal portions of definite length and weight. It appears that they're saying that the particle nature of light, the photon, is only an appearance. But they tell us, quote, and practically considered, that is what happens, unquote. This is a bit confusing. Is it just appearance, or is the dual nature of light a reality? Our physicists early on decided that light is a particle under some circumstances, but a wave under other conditions. Some have called the photon a wavicles because of this. Experiments have proven this dual nature of light. And quantum mechanics informs us that whether light behaves as a wave or particle can also depend on whether or not we attempt to measure its state. The strange things that happen at the quantum level seem to speak of a reality behind appearances. Perhaps the unseen influences are, as the authors say in paragraph 8, quote, the presences, the performances, and the coordination of the conjoint actor and the unqualified absolute, unquote. Section 6, Calcium, the Wanderer of Space. I find this section somewhat problematic. It appears that it is largely derived from Eddington's book, Stars and Atoms, as is much of the rest of Paper 41. But what Eddington presents as theories, the authors of the Urantia papers present as fact. In the second paragraph of Section 6, the authors state, calcium is in fact the chief element of the matter permeation of space throughout Urantia. Our whole super-universe is sprinkled with minutely pulverized stone, unquote. After decades of astronomical observations and measurements, astronomers know that interstellar space contains mostly hydrogen, a much smaller amount of helium, and about 1% of cosmic dust. A quick internet search will confirm this. It is true that there are traces of calcium and other elements in interstellar space and interplanetary space, but they are only minute amounts. In paragraph 3, the authors tell us that this calcium atom moves outward by alternate jerks of forward propulsion, grasping and letting go the sunbeam about 25,000 times each second. Eddington states on page 70, the art of riding a sunbeam is evidently rather difficult because only a few of the elements have the necessary skill. The most expert is calcium. The sunlight traveling outwards carries a certain outward momentum. If the atom absorbs the light, it absorbs also the momentum and so receives a tiny impulse outwards, unquote. On page 72, he expands this a bit. To accommodate the extra energy, the electron is tossed up into a higher orbit. This method is called excitation. After remaining in the excited orbit for a little while, the electron comes down again spontaneously. The process has to be repeated 20,000 times a second in order to keep the atom balanced in the chromosphere. On page 73, he tells us, the average time occupied by each performance is 1/20,000th of a second. On page 74, he says, the higher orbit remains there for an average time of 100 millionth of a second before it spontaneously drops back again. I may add that during this brief time it makes something like 1,000,000 revolutions in the upper orbit, unquote. Eddington's text is similar enough to that of the Urantia Book that it does appear to be the source text. But note that Eddington does not say that the calcium atom grabs onto the sunbeam, but he does mention the calcium atom riding the sunbeam. But this is a metaphor, not the literal explanation that involves the atom absorbing light energy. Further on, he says that the atom absorbs an increment of light energy, and this causes the electron in the outermost orbit to jump to a higher orbit, then it drops back down, emitting another photon. Eddington's theory is that the emitted light in the upward direction has lost more energy than the light emitted in the downward direction, so on average the calcium atom gets a net upward force. Also in paragraph 3, the authors mention a calcium layer, a gaseous stone-lit surface, unquote, that is 6,000 miles thick. This would have to be the chromosphere. In fact, astronomers' measurements show that the primary component of the chromosphere is hydrogen, though calcium and several other elements are certainly present in small amounts. Eddington says that the layer of calcium suspended on the sunlight is at least 5,000 miles thick, but he does not say that it is a principal element in the chromosphere. The current slide has a cross-section of the sun showing the location of the chromosphere layer. Paragraph 4 of this section of Paper 41 asserts that stone, calcium, is the chief component of the worlds of space. The table in the current slide shows the composition of the Earth. Calcium represents only 1.5% of the Earth's volume. Note that the authors use the term stone interchangeably with calcium in this section for some unknown reason. Section 7, Sources of Solar Energy. The authors tell us in Section 7 that the surface temperature of the Sun is 6,000 degrees Fahrenheit, which agrees with the measurements that astronomers have made. However, the authors say that the temperature at the center of our Sun is about 35 million degrees Fahrenheit, and they say that this number is much higher than our physicists thought at the time. Sources on the internet cite the temperature at about 26 million degrees Fahrenheit. Eddington says that the temperature at the center of the Sun is 40 million degrees Fahrenheit, and obviously this number is larger than that cited in Section 7. Of the 7 sources of solar energy listed in paragraph 3, our physicists would no doubt recognize only part of them as shown on the slide. They might go along with energy released by annihilation of atoms, but not electrons, since they believe that the electron is itself a primary, indivisible particle. Since the energy circuits are unknown on Urantia, our physicists would have no way of knowing that our sun may get energy from this source, and it's not clear what the circuitized power is that they mention in source number 6. When the authors speak of the regulating blanket of gases, they evidently mean the corona, which does reach millions of degrees according to our astronomers. The current slide shows how the corona appears during an eclipse of the sun. As the authors assert, the output of the sun has been very constant, at least over the time that our physicists have been monitoring its output. It does show a variation of about 0.1% from the sunspot minimum to the sunspot maximum of the 11.5-year cycle. In paragraph 6 of this section, the authors state that 1 drop of water contains as much energy as 100 horsepower applied for 2 years. In his book, Stars and Atoms, Eddington has this to say: by annihilating a single drop of water, we should be supplied with 200 horsepower for a year. This is on pages 102 and 103. Note that 100 horsepower for 2 years represents the same amount of energy as 200 horsepower for 1 year. The current slide shows the calculated energy for 100 horsepower exerted for 2 years and the energy in a drop of water using the author's figure for the number of atoms of water, over 1 billion trillion. In his book, Eddington gives the number of atoms in a drop of water as several thousand million atoms. Eddington's number, and that in the Urantia book, would be something like n times 10 to the 21st power, where n could be several or more than 1. So in essence, the authors used Eddington's number. The results indicate that Eddington's numbers and calculations are correct. The authors state that some suns will go on forever because they receive energy from the energy circuits that course throughout the universe. Unfortunately, suns that can't receive energy from the universe circuits are destined to burn out. They do not tell us whether our sun is or is not one that will burn out. They state that stars that aren't recharged are eventually disrupted by mass explosion. According to physicists, all stars go through a red giant phase as they age. Low-mass stars do not go into supernova as they approach their end stage. They simply lose their outer layers and end up as a white dwarf star. But stars that are more than 6 times as massive as our sun can explode as a supernova at the end of their normal life. Once these higher-mass stars experience a supernova, they end up as a white dwarf, a neutron star, or a black hole, depending on the mass of the remnant core, as shown on the slide. This completes the lecture on sections 5, 6, and 7 of paper 41.